Okay, this is lecture 34. We're going to be talking about some of the terminology for continuous time Markov chains. So let me remind you about some of the terminology that we've actually already seen in the previous lectures. So embedded chain was one of these. If you just look at, so continuous time Markov chain, remember the big thing with continuous time Markov chains is that you stay in a state for a continuous amount of time. So it doesn't transition from one state to another in a fixed amount of time. And so, but one of the things that you tend to look at is which states is my current state going to go to. So if you just watch the sequence of states, so if you just watch which state state I goes to afterwards, so like if I goes to J, etc., you can think about the sequence of state transitions, and this is what's called an embedded chain. So this is actually a discrete time Markov chain that kind of describes the just where you would transition in your continuous time Markov chain. So we let T stand for this transitions matrix for this embedded chain. So here's the probability that you're going to transition from I to J. And so remember we talked about how you actually find this transition matrix. So if you know the rate at which you transfer from one state to the other, then you can take the rate divided by the sum of all the rates out of state I. So anyway, we have this embedded chain and we have this transition matrix for it. And remember that this T is a stochastic matrix whose diagonal elements are actually 0 in this case. So the other things that we've talked about already is the transition function. So the transition function is given by P of T, which is the probability of going from state I to state J in time T. So we, in addition to our embedded chain T and our transition function, we also have this infinitesimal generator. So remember the infinitesimal generator is this matrix in which the off diagonals are our rates going from one state to another. And one of the ways that we can actually find this is we can, in the way it's related to our transition function, is that our infinitesimal generator Q is equal to P prime of 0. It also satisfies these differential equations. dP dt is equal to Qp and dP dP is equal to PQ. And so looking at it this way, we can actually write, if we know our Q, then we can find our transition function by just saying it's e to the Qt. And we talked about some different ways of finding e to the Qt in the previous lecture. Okay, so we're going to relate a lot of things to our discrete time Markov chain because you already know a lot about that. You've worked with that for several weeks now. So just remembering some of the terminologies for discrete time Markov chain. We talked about a state being accessible, the state J being accessible from state I. So basically, if I can go to J, even if it's not directly to J, but if I can go through some other states and get to J, then it's called accessible. And if I communicates with J and J communicates with I, if I is accessible from J and J is accessible from I, then basically you say they communicate and they're in the same class. So here we have this terminology that I communicates with J. And then we talked about what are called irreducible Markov chains. And so irreducible Markov chains were when there was only one communication class. So basically every single state communicated with every other state. And a set of states is closed if you're in that state and you can't reach any of the other states outside of it. You say that your set of states is closed or your class is closed. So the way we're going to relate this is, remember the embedded chain is a discrete time Markov chain. So this embedded chain that's related to our continuous time Markov chain actually tells us a lot about our continuous time Markov chain. So let's talk about some of the terminology for continuous time Markov chains. So here in a continuous time Markov chain, we said I and J communicate if and only if I and J communicate in the embedded Markov chain. So basically, if you look at the embedded Markov chain and you have that I and J communicate, then you say that they communicate for your continuous time Markov chain. So the embedded Markov chain is going to give us a lot of information. So in addition, we can say this generator matrix Q in a continuous time Markov chain is irreducible if and only if our transition matrix T for the embedded chain is irreducible. So again, this embedded chain is really important. If we have our embedded chain is irreducible, then we basically say our continuous time Markov chain is also irreducible. So here we have a theorem. We have that state I in a continuous time Markov chain is recurrent or transient if and only if the state I in the corresponding embedded chain is recurrent or transient. So basically, if in your embedded chain you have that state I is recurrent or transient, then you also have the same thing in your continuous time Markov chain. So basically, our state I in a continuous time Markov chain is recurrent if and only if the sum of the ti raised to the n. So remember, this is the ii element raised to the nth power is equal to infinity. Okay, so for a finite Markov chain, all states can't be recurrent. There have to be all states can't be transient. There have to be some that are recurrent. And so remember, we talked about the Poisson process, which is the counting process, the number of arrivals. For a Poisson process, each state I can only advance to state I plus 1, so you can't actually return to state I. So every state is transient in a Poisson process. So why doesn't that counteract this? All states cannot be transient because the Poisson process is not finite. A Poisson process is infinite. So here, this is an example of an infinite continuous time Markov chain in which it is transient. You can never go backwards. So a finite Markov chain, if a finite Markov chain is irreducible, then it's also called recurrent. So if we have, so talking about limiting distributions, if we have a finite and irreducible continuous time Markov chain that has our transition function P of t and generator matrix Q, then, now this is for finite and irreducible, then there's a unique stationary probability, just like we have with discrete Markov chains. There's a unique stationary probability distribution where Q pi is equal to 0, and the sum of all of our states here is equal to 1. And so basically we say here the limit as t goes to infinity of p I j of t, the probability of going from I to j of t, is equal to pi I. So this is our stationary limiting distribution for our state I. And this is going to be equal to -1 over qii. So this is our transition, this is our diagonal element for our generator matrix times mu ii. Where here we're going to talk about mu ii, and we're going to I'm going to tell you what that is in just a second. But this is, I want to stress that this is for finite irreducible continuous time Markov chains. In general, there are stationary distributions that are not limiting, and there are limiting distributions that are not stationary. So for finite irreducible Markov chains, continuous time Markov chains, then we have this unique stationary probability distribution. And here, this mu ii is actually our, and I don't think I said it here, but it's going to be our time to get back. So let's look at an example here. So let the Q be this matrix here. So this is our generator matrix. So then we can define P of t as e to the qt. There's a way to actually rewrite this. So if we look at just what happens if we take q squared, so q squared is just q times itself, and we look at this, we have a plus b in common in every single term. And so we can factor out, when we actually factor out a minus a plus b, and we're left with negative a, b, a negative b, which is the exact same as our Q matrix. And what we can notice in general is that if we actually raise this to the nth power, then we have this negative a plus b to the n minus 1 power times our original matrix Q. So what that means is we can actually look at our e to the qt. When the summation, we can actually replace the summation of the q to the n with this formula. So here's our q to the n formula. So we can say this is equal to I plus, and so now we can think about this being raised to the n divided by one of those. And so the reason why we're doing this is because we're going to combine this t and this a plus b together. So here we have the negative a plus b to the n and t to the n combined together into 1. And we just bring out this minus q over a plus b. And this summation, if you remember from Calc 2, this summation is just e to the negative a plus bt. So we can find the limit as t goes to infinity of p of t. So we can find our limiting distribution by looking at the limit as t goes to infinity of this. So this is just I plus 1 over plus q over a plus b, because this part goes to 0. So all we're left with is the negative 1 times this. So here's this. Well, just writing down what this is, this simplifies to this thing. So we notice that our pi is just going to be our columns here, our BA, times this 1 over a plus b. So we can find the mean recurrence time. We have, going back to that definition, our pi I is negative 1 over our diagonal element in our generator matrix times our mean recurrence time. So the mean recurrence time is given by this negative 1 over qii pi I. So for our example, we have that the mean recurrence time for state 1 here is just a plus b over ab. And for state 2 is a plus b over ab, the same. So from the previous lecture, we had this matrix Q. And this is the one that we actually used Maple on. So we had this matrix Q. And we can actually write down, if you look, we can write down what the embedded Markov, the embedded chain looks like. So here, what does this say? This says that Q only transitions to its, 1 only transitions to 2, 2 only transitions to 3, 3 only transitions to 4, and 4 only transitions to 1 here. And we had e to the qt from Maple was given by this, and so if we look at this part, and we take the limit as t goes to infinity, what's going to happen? Well, this goes to 0. This one here goes to 0, so we're just left with this first matrix. So the limit as t goes to infinity of p of t is just given by this 1/4 times this matrix of 1s. So the stationary distribution is just 1/4 for every single state. So this gives us a mean recurrence time is negative 1 over qii. So all of our qii's were negative 1, so all of our mean recurrence times are 4. Okay, one other example. So here, this is an example of a continuous time Markov chain. So if we look at this, we can calculate e to the qt. So different ways of calculating e to the qt, but so if we calculate e to the qt, we can get this matrix here. Now if we look at our earlier theorem, it doesn't apply because q is not irreducible. So here, if we look at this, our q is not irreducible. Here actually we have a state goes to itself, right? So here we have state 1 always goes to itself, so this is an absorbing state, so it's not irreducible. Notice what our limits go to. So if we take the limit as t goes to infinity, this is 1, 0, 0, 0, right? So are all of these. So this limits to 1, 0, 0, 0. This limits to 1, 0, 0, 0, etc., etc. So all the columns of E of qt approach this 1, 0, 0, 0, just like we kind of had with the powers, that we had things that were approaching pretty much the same thing. All the states are absorbed into state 1. So this is what our transition diagram would look like. Okay, so next time we're going to give an example of how you actually use this terminology in a problem.